I am looking at the spectral analysis on my monitor right now, and for the 10th time in the last hour, I am trying to convince myself that there is a calibration error. It is 2 a.m. here in the observatory, the coffee is cold, and the hum of the cooling fans in the server room is the only thing keeping me grounded in reality, because what I am seeing in this data, what the James Webb Space Telescope has just beamed back to us regarding the object we are calling 3I Atlas, does not belong in a standard cometary model. It does not belong in our understanding of planetary formation. Honestly, it barely belongs in this solar system. We have been tracking this visitor since July, and every single time we think we have a handle on what it is, it throws something new at us. But this material signature is different. We aren't just looking at exotic ices anymore. We are looking at something that, by all the rules of stellar nucleosynthesis and geological differentiation, shouldn't be floating alone in the void in this specific purity. Let's back up, because to understand why this specific spectral line is causing me to question my graduate studies, you have to understand the journey we have been on for the last 6 months. It started on July 1st, 2025. The Atlas survey in Chile, the unit in Rio Hurtado, pinged a new transient object. At first, nobody panicked. We see new comets all the time. The automated systems flag them, we calculate an orbit, and usually, it turns out to be some chunk of rock from the Oort cloud that got nudged inward by a passing star or galactic tide. We call them long-period comets. They fall in, they sizzle, they swing around the sun, and they leave. Standard procedure. But the alerts kept upgrading the priority level. Within 48 hours, the orbital parameters were refined, and the eccentricity numbers started coming in. For those of you who don't spend your lives staring at orbital mechanics software, eccentricity is a measure of how stretched out an orbit is. A perfect circle is 0. A very stretched ellipse, like a normal comet, is close to 1. Anything above 1 means the object isn't bound to the sun. It's a visitor. It's just passing through. Oumuamua, the first interstellar object we found back in 2017, had an eccentricity of about 1.2. It was fast, and it was definitely not from here. Borisov, the second one in 2019, was around 3.3. 3I Atlas came in with an eccentricity of 6.2. When I first saw that number, I assumed it was a glitch in the astrometry. You don't see numbers like that? A value of 6.2 implies a hyperbolic excess velocity. That's the speed it has when it's infinitely far away from the sun, of nearly 60 kilometers per second. This thing wasn't just drifting through the galaxy, it was being shot out of somewhere like a cannonball. It punched through the plane of our solar system with such kinetic violence that it barely seemed to notice the sun's gravity. It didn't curve much, it just sliced through. By late July, we knew we had the third interstellar object in history. We designated it 3I. The excitement was palpable, but it was also guarded. Oumuamua had been a frustrating ghost, a dark, tumbling cigar or pancake that accelerated without any visible gas, leading to wild theories about solar sails and alien artifacts. Borisov had been the opposite, a surprisingly normal comet that just happened to be from another star. It had water, it had dust, it behaved exactly like a comet from our own backyard, so the community was split. Would 3I be another ghost or another snowball? It turned out to be neither. It is something entirely its own. As 3I Atlas approached the inner solar system in August and September, we threw everything we had at it. The Vera Rubin Observatory, which has been a game-changer for deep-field surveys, started tracking its light curve. We realized it wasn't tumbling chaotically like Oumuamua. It had a stable rotation, roughly every 16 hours. It was large, too. Estimates hovered between 2 and 5 kilometers wide, making it significantly beefier than our previous visitors. But the real surprise came when it crossed the orbit of Mars in early October. We got lucky, and I mean astronomically lucky. The geometry of the approach brought 3I Atlas relatively close to Mars, just as the planet was positioned for optimal viewing from Earth-based assets. But more importantly, we had spacecraft in orbit around the red planet. The Mars Reconnaissance Orbiter and the European Space Agency's Trace Gas Orbiter were able to slew their instruments and catch a glimpse of this intruder. They saw a coma, a halo of gas and dust. 3I was active. This was the moment the comet faction declared victory. If it has a tail, it's a comet. It's a dirty snowball sublimating in the heat of the sun. Case closed, right? But as the data packets from the TGO arrived, the picture got complicated. The coma wasn't water vapor. In our solar system, comets are mostly water ice. When they get close to the sun, that water turns to gas and drags dust with it to form a tail. But the spectral analysis of 3I's coma showed almost no water. It was dry. Instead, it was pumping out massive amounts of carbon dioxide. The CO2 to water ratio was nearly 20 to 1. That is unheard of. It's like finding a desert that is raining pure soda water. This anomaly suggested that 3I Atlas formed in a place very different from our own solar system. To get that much CO2 and that little water, you need to form in a specific snow line of a planetary disk, perhaps around a star that is cooler or richer in carbon than our Sun, or it implies that the object has been baked by cosmic rays for so long that the water on its surface has been stripped away, leaving a crust of dry ice. But even that didn't prepare us for what we found when we pointed the big guns at it. I was part of the team that was granted discretionary time on the James Webb Space Telescope in late November, just a few weeks ago. We wanted to look at the fingerprint of the gas, the emission lines that tell us exactly what elements are popping off the surface. Spectroscopy is the heart of modern astronomy. Every element in the universe, when heated or excited, emits light at very specific, unchangeable wavelengths. It's a barcode. Hydrogen has a pattern. Carbon has a pattern. Iron has a pattern. When we look at a star or a comet, we read these barcodes to tell what it's made of. We pointed the near-infrared spectrograph at 3I Atlas, expecting to see the usual suspects: carbon, oxygen, maybe some sulfur or nitrogen, and we did see those. But then, we saw a set of emission lines in the ultraviolet and near-infrared that made no sense. They were lines for nickel, neutral nickel vapor. Now, finding metal in a comet isn't completely impossible. We've seen traces of heavy metals in comets like Ikeya-Seki, which grazed the sun so closely that the rock itself started to vaporize. But 3I Atlas wasn't grazing the sun. It was passing at a comfortable distance just inside the orbit of Mars. It wasn't hot enough to vaporize solid metal rock. Yet, there was the signal, screaming at us: nickel. But here is the kicker. Here is the thing that keeps me awake at night. In nature, in every asteroid, every comet, every star, and every dust cloud we have ever analyzed, nickel is always found with iron. They are cosmic twins. They are formed together in the hearts of dying stars and supernovae. Iron is usually about 10 times more abundant than nickel. If you see nickel, you should see a massive, blinding signal for iron right next to it. It's the law of the cosmos. We looked, we checked the data, we recalibrated the instrument, we looked again. There is no iron. The spectrum shows a strong, clear abundance of nickel, but the iron lines are completely absent. The ratio is broken. It's not just slightly off, it's non-existent. It's like finding a human skeleton made entirely of titanium. It shouldn't exist in a natural state. This discovery, which we are still writing up and arguing about in closed-door meetings, changes everything about how we view 3I Atlas. If this were a natural object, a shard of a protoplanet, the iron and nickel should be mixed in an alloy, like the iron meteorites we find on Earth. To separate them, to get pure nickel or a nickel-rich gas without iron, requires a process that differentiates them. On Earth, we do this in smelters. We use chemistry and heat to refine ores, stripping away the impurities to get the metal we want. In space, this differentiation happens in the cores of massive planets, but even then, the iron and nickel sink together. To have a cloud of gas around a comet that is rich in nickel but devoid of iron implies one of two things, and both are terrifying in their own way. The first possibility is that we are looking at a completely new type of stellar chemistry. Perhaps 3I Atlas originated from a system centered around a star we don't fully understand. Maybe an asymptotic giant branch star that has a specific nucleosynthesis pathway that suppresses iron production or traps it in a form that doesn't sublimate, while allowing nickel to escape. There are theoretical models, obscure papers from the 1990s, that suggest certain S-process environments could create isotopic anomalies. But to this scale? To the point of total separation? It would require a parent body that formed in a part of the galaxy with a chemical history completely alien to our own. It suggests that the average composition of the universe is not as average as we thought. The second possibility is the one we whisper about in the break room but hesitate to put in the abstract of the paper. It's the artifact hypothesis. I am a scientist. I rely on evidence, not science fiction, but we have to look at the data objectively. If I handed you a block of aluminum, you would assume it was manufactured because pure aluminum doesn't occur naturally. It's always bound up in bauxite. If we see a cloud of pure nickel gas, we have to ask, is this the result of an industrial process? Is 3I Atlas the wreckage of something? We aren't seeing a smooth, natural outgassing. The coma is weirdly symmetrical, and the jets we are seeing, the plumes of material shooting off the surface, are concentrated. The VLT in Chile took images that show the coma doesn't have the chaotic, wind-swept look of a normal comet. It looks organized, And now, combined with this material anomaly, the nickel without iron signature, it feels like we are looking at the exposed internals of a mechanism, or perhaps the hull of a vessel that has been eroded by billions of years of interstellar travel, bleeding its component metals into the vacuum. I want to be clear, I am not saying it is aliens. As Carl Sagan said, extraordinary claims require extraordinary evidence, and a weird spectrum is not a handshake, but it is a material scientists haven't seen on a visitor before. It challenges the assumption that interstellar objects are just rocks. Rocks are messy mixes of everything. This object is chemically specific, it is refined, and the timing adds to the drama. As I speak, it is December. 3I Atlas is nearing its closest approach to Earth. It's about 1.8 astronomical units away, safely distant, about twice as far as the Sun, but it is bright enough for us to get this data. We have a window of maybe 2 more months before it fades into the dark, heading back out toward the constellation of Sagittarius. It's moving so fast that we cannot catch it. There is no rocket in our arsenal that can launch today and match a speed of 60 kilometers per second. We have to sit here and watch it leave. However, the material mystery is deepening. Just yesterday, another dataset came in from the Psyche mission. The spacecraft is currently in the asteroid belt, en route to its own metal world, but it turned its cameras back toward the inner solar system to watch 3I pass. Psyche's multispectral imagers are designed to spot metal. That's their whole job. They picked up a reflectance signature from the nucleus of 3I Atlas that matches the spectral slope of, well, it looks like a specific type of carbonaceous chondrite, but wet. This contradicts the CO2 data. Remember, the gas says dry, but the surface reflection says wet or hydrated minerals. How do you reconcile that? The leading theory developing this week is that the object has a crust, a shell. The surface is a baked, organic-rich sludge, tholins we call them, that looks like dark, red tar. This crust might be trapping the volatiles inside, but the nickel might be coming from under that crust. Imagine an object with a metallic core shielded by layers of ice and organic goop. As it gets close to the sun, cracks form in the crust. The heat penetrates deep, skipping the surface layers, and sublimates a specific layer of frozen gas near the core. If that core is a shard of a shattered planet's mantle, maybe, just maybe, we are seeing the breath of a dead world. This brings us to the cryovolcanism aspect. The images from the last few weeks show that the brightness of the object isn't steady. It flares, it pulses. This suggests explosive events. Pressure builds up under that strange crust and bang, a jet of gas erupts. This fits with the high CO2. Carbon dioxide ice can be explosive when it sublimates in a confined space. But again, why the nickel? Why is the gas carrying a heavy metal that should be locked in stone? Some of my colleagues are looking at what we're calling organometallic compounds. These are complex molecules where a metal atom is bonded to carbon atoms, and although the term sounds exotic, it shouldn't be. In Earth biology, we already rely on organometallic chemistry in ways people rarely appreciate. Hemoglobin, the oxygen-carrying molecule that keeps you alive, uses iron at its core. Chlorophyll, the molecule that lets plants drink in sunlight, uses magnesium in the same elegant configuration. Industrial chemistry is full of nickel-bearing catalysts. So when we look at the spectra from 3I Atlas and see certain absorption features and emission lines that hint at metal-carbon complexes, we're forced to consider an uncomfortable possibility. Maybe what we're observing isn't just a cloud of dust or some sputtering gases from a simple comet. Maybe it is a cloud of broken-down complex molecules, something that stretches the boundary between organic chemistry and planetary geology. Something that suggests a chemistry that feels prebiotic or possibly even postbiotic, depending on how bold you want to be with your imagination. If 3I Atlas is truly spewing out nickel-bearing organic chains, if these molecules really are long, carbon-rich structures with metal centers, then we aren't just observing debris. We are, in a very real sense, receiving a chemical sample vial from another star system. It's as if the universe reached across light years and handed us a bottle full of clues. The more I stare at the data, the more this metaphor feels literal. Every strange spike in the infrared spectrum, every odd fluorescence feature in the ultraviolet, it's all whispering something that we haven't learned to translate yet. We are scrambling to get time on the Deep Space Network to listen for radio transmissions. We know it's a long shot, not even a long shot, it's the longest of long shots, but we feel compelled. We did the same for Oumuamua, and all we heard was the cosmic background humming like an old refrigerator in a quiet room. No patterns, no pulses, no signature of intentionality, and now we're doing it again for 3i, partly because we don't want to miss anything, partly because the strangeness of this object demands that we eliminate every possibility, even the ones we barely take seriously. So far, there's nothing but the static hiss of the cosmic background radiation, the sound of a universe that existed long before we had ears to hear it. But even with the radio silence, the visual and chemical data feel deafening. It's loud enough to challenge us, to unsettle us, to remind us we haven't mapped the borders of what's possible. There is another aspect to this material that is baffling the dynamicists, the scientists who specialize in orbital mechanics, the movement of objects through gravitational fields. Normally, when a comet shoots out gas, it acts like a natural thruster. Outgassing produces jets, and those jets push the nucleus in measurable ways. We call this non-gravitational acceleration. Oumuamua famously displayed this behavior. It drifted and wandered as if someone were tapping it from behind with gentle, invisible fingers. But 3i Atlas is refusing to play by those rules. Despite releasing all this CO2, all these nickel-bearing gases and weird organometallic fragments, it's moving almost purely on gravity. No drifting, no wobbling, no detectable push. It just glides along the path predicted by Newton and Einstein, as if it were a solid, inert mass with no jets at all. This is profoundly strange. To have a large, active comet that shows zero non-gravitational acceleration implies that the nucleus is extremely massive, much more massive than a ball of ice should ever be. If the outgassing isn't moving it, that means the object must have enormous inertia. It must be dense, heavy in a way that common cometary material isn't. This reinforces the growing suspicion that we are dealing with something disguised as a comet, a dense object wrapped in a thin, evaporating coat of volatiles, a solid metal chunk, a super-dense alloy, a fragment of something much larger, something forged in conditions we haven't replicated since the earliest moments of the universe. I am sitting in the dim glow of my office monitors, staring at the stacked spectra on the screen. I zoom into the 3200 angstrom region where the nickel lines are screaming like neon signs. There's a beauty to it, a kind of harsh elegance. These glowing, sharp emission lines feel like a message written across the electromagnetic spectrum, a message that says, you don't know as much as you think you know. It's humbling, it's exhilarating, it's terrifying. Every scientist privately hopes for data that surprises them, but this is something beyond surprise. This is data that shakes the foundations of our assumptions. The plan for the next few weeks is intense. As 3i Atlas moves farther from Earth and the Sun, the geometry of its illumination will shift. That means that, for the first time, we'll be able to see the object's night side using space telescopes, JWST, Hubble, and a few lesser-known instruments that excel at thermal infrared imaging. We want to know whether the outgassing is happening everywhere or only on the sunlit side. If gas is being expelled from the dark side, then the heat is being retained deep inside the object, stored in its thermal mass rather than instantly radiating away. Metals are fantastic heat conductors. They soak up energy and distribute it evenly. Ices, on the other hand, are terrible at storing heat. They warm up only at the surface. So if the night side of 3i Atlas glows in the infrared, if it radiates like a stove burner that's been turned off but not cooled down, then it will be yet another piece of evidence for what some of us are now calling the metal world theory. It would mean we aren't just dealing with a rock or an ice ball. We may be studying a metal-rich body from another star system, something more akin to a fragment of a differentiated planet, like the metallic core of a shattered world that has drifted across interstellar space for an unfathomable amount of time. We're also analyzing the polarization of the light reflected off the object. Polarization is subtle but incredibly informative. When light bounces off a rough, porous surface, like a dusty comet, the polarization signal looks one way. When light reflects off a smooth, metallic surface, it looks very different. Early polarization data is messy, corrupted by interference, noise, and the difficulty of observing something so faint and fast-moving. But even through the chaos, hints are emerging. The object seems to have a surface that is unbelievably dark, absorbing 95% of the light that hits it, yet with occasional patches of high reflectivity. It's like looking at a stealth aircraft coated in radar-absorbing material, except with scratches or polished areas where the underlying metal peeks through. That combination, extreme darkness with intermittent metallic glints, is deeply peculiar. Comets tend to be dark, yes, but they aren't this dark, and when they are reflective, it's usually because of ice. Ice doesn't reflect light like polished metal. It scatters it in soft, diffuse patterns. This object shows sudden spikes of sharp reflection, like mirrors catching starlight. The contrast is so extreme that even our seasoned observers are at a loss. It looks like someone tried to hide the object, then didn't bother to hide all of it. As all this is happening, we continue to refine our models, and I find myself drifting into long, unsettling thoughts late at night. I wonder what kind of world this fragment could have come from, if it is metal-rich, dense, irregularly coated with dark material, and outgassing organometallic compounds. Then what was its parent body like? Was it a planet that had an active mantle full of exotic chemistry? A moon orbiting a gas giant with tidal heating that pushed its chemistry into strange new directions? Or was it something even stranger, a body whose surface was repeatedly reworked by impacts, creating pools of molten metal that cooled into alloys unknown on Earth? There's also the question of time. How long has this object been traveling? Interstellar space is vast and corrosive in a subtle way. Micrometeor strikes, cosmic rays, UV radiation, over millions or billions of years, they wear down even the toughest materials. But this object doesn't look worn down. It looks relatively intact. Sharp angles, hard edges, reflectivity that shouldn't exist if the surface spent millions of years being sandblasted by relativistic particles. That implies one of two things. Either the object hasn't been traveling through space for long, an astronomical blink, perhaps only a few 100,000 years, or it is made of something that resists erosion in ways we don't fully understand. That possibility makes some of us uneasy. A short interstellar travel time means it was ejected recently on cosmic scales. That could imply a catastrophic event in a nearby stellar system, an impact, a breakup, a nova, something dramatic enough to fling debris across light years. And if that's the case, we're not merely studying an object. We're studying the aftermath of a stellar tragedy. I think about the organometallic compounds again, about the possibility that they represent chemistry on the verge of life, or chemistry left behind by processes we no longer recognize. Prebiotic molecules are one thing, but complex metal-bearing chains that don't behave like naturally forming interstellar dust, that's something else. It forces me to rethink the line between natural and artificial. The universe doesn't owe us clarity. It doesn't label things. It doesn't separate the organic from the inorganic in neat categories. So when we see something that blurs the boundary, we're left fumbling, trying to decide whether nature is being extraordinarily creative, or whether we're staring at the debris of processes that once involved living systems. Late at night, when the lab is quiet and the only light comes from the screens, I zoom in on the oddest parts of the spectra. I imagine the molecules that might produce these signals. Nickel surrounded by carbon rings, carbon chains branching in ways we don't see in Earth biology but could imagine arising in some alien environment. I picture them vibrating and spinning, absorbing light, emitting light, tumbling through vacuum. I imagine them as relics of something long gone, carried by this silent metal traveler. And sometimes I think, what if these molecules were never alive but once supported something that was? What if they're leftovers, the crumbs of a vanished ecosystem? Meanwhile, the dynamicists are growing increasingly frustrated. Every new set of trajectory measurements confirms the same thing. The object is too stable, too heavy, too indifferent to its own outgassing. It behaves less like a comet and more like a small asteroid, or even a fragment of a metal-rich protoplanet. A few have joked that maybe we're looking at alien industrial waste, literal garbage from a faraway civilization. We laugh, but there's a nervousness beneath the humor. Not because we actually think it's garbage, but because the situation is so weird that even absurd explanations feel marginally less absurd. As 3I Atlas moves farther away, its tail elongates and thins. The outgassing continues, but the density of material in the coma decreases. Yet the chemical composition stays consistent. CO2, nickel, hints of organic carbon structures. Nothing like this has ever been documented in a natural solar system object. Some of the youngest grad students in the department are starting their careers at the perfect time. They get to witness something unprecedented, something that might rewrite the textbooks they studied just a few years ago. I envy them in a way. They get to shape the narrative. We merely watch it unfold. Soon, we'll get the deep infrared data, microthermal variations, surface conductivity patterns, maybe even subtle seismic signatures inferred from thermal stress. If the object responds to heating like metal, fast conduction, slow re-radiation, that will be another nail in the coffin of the ordinary comet model. And if we find that the dark coating behaves like carbon black or graphene-like material, it might explain the extreme darkness. Graphene absorbs nearly all incoming light. If meteoritic processes in another star system produced a thin film of carbon sheets, layered, fragmented, chaotic, it could create a natural stealth surface. That idea has been bouncing around the group. No one wants to say it outright because it sounds too dramatic, too science fictional. But carbon structures do amazing things when given enough time and energy. As the days pass, I find myself oscillating between excitement and dread. Excitement because we are on the brink of something extraordinary. Dread because extraordinary discoveries rarely arrive without shattering something. An assumption, a theory, a sense of comfort. We like to imagine that the universe is understandable, predictable. But then something like 3I Atlas drifts in from deep space and reminds us that our understanding is provincial, local. A product of growing up in one solar system with one set of materials and one tiny slice of cosmic diversity. Sometimes I imagine 3I Atlas as a messenger. Not an intentional one, not something sent with purpose, but a messenger in the geological sense. A shard, a broken piece, a token of a world we will never see. And as it speeds away, growing dimmer by the day, I feel a strange sadness. Because we only get to see it once. It will never return. Its path is hyperbolic. Gravity will never curve it back toward us. This encounter is a single moment in time, and all our instruments, all our efforts, all our desperate attempts to understand are happening in the narrow window before it slips away forever. The more I think about it, the more I realize how fragile this opportunity is. We are trying to decode an entire planetary history, an entire stellar context, from a few weeks of data. It's like trying to understand a person's life from the sound of one footstep. But even one footstep can tell you something: the weight, the stride, the texture of the ground. So we listen to 3I Atlas as carefully as we can, hoping the echoes will reveal something profound. And deep down, despite the radical ideas floating in my mind, metal worlds, organometallic clouds, strange chemistry, stealth coatings, I remind myself that nature is allowed to be surprising. Nature is allowed to invent things we haven't seen before. We don't need aliens to explain the extraordinary. The universe itself is extraordinary enough. Still, I can't deny the feeling, a quiet, persistent whisper in the back of my mind, that whatever 3I Atlas is, it's telling us something important. Not in words or signals, but in its silence, its density, its strange chemistry, its refusal to behave like anything we thought we understood. Maybe the message is simple. The universe is bigger than our imagination, and we've only just begun to discover the kinds of worlds that exist beyond our own. As the nickel lines continue to blaze in the ultraviolet and the object drifts toward the outer planets, I sit in the dark, watching data stream in pixel by pixel, photon by photon, and I feel privileged, almost overwhelmed, to witness a moment like this. A moment when the universe lifts a corner of its veil and lets us see a new kind of object, a new kind of story, a new chapter in the endless mystery of what lies between the stars. I try to keep my imagination in check. I really do. But when you are alone in the observatory, looking at light that has traveled for millions of years from a star system we will never visit, bouncing off an object that is currently sailing past our own planet, you can't help but wonder, what if the missing iron isn't missing? What if it's just being used? What if the nickel is the waste product, the exhaust, and the iron is the structure? No, that's too far. Stick to the science. The science says we have a hypervelocity object, eccentricity 6.2, origin Sagittarius, composition rich in CO2 and oddly enriched in pure nickel gas. It is a material profile that fits no known class of solar system body. It is a unicorn. In the coming days, you will see headlines. Some will scream aliens, some will scream Planet 9 debris, some will just say weird comet. But pay attention to the specific mentions of the elemental composition. That is where the real story is. The geometry of the orbit tells us where it came from, but the spectrum tells us what it is. And right now, what it is a mystery that is rewriting the textbooks on material science in the void. We are realizing that the galaxy is a much more diverse factory than our local bubble led us to believe. We assumed comets were universal. We thought they were all the same dirty snowballs. 3I Atlas is teaching us that interstellar space might be filled with shrapnel from events we can barely model, shredded cores, ejected crusts, or things even stranger. I have to get back to the data reduction pipeline. We have a new download coming from the Hubble Space Telescope in 20 minutes. Hubble is old, but its UV sensitivity is legendary, and it might just give us the clue we need to solve the nickel puzzle. Whatever 3I Atlas is, it is waving goodbye. It will never return. We have one shot to understand it, and I intend to spend every minute of this encounter trying to figure out why a visitor from the stars is dusting our solar system with a material that shouldn't be there. This is the reality of modern exploration. We don't sail ships to new islands anymore. We catch fleeting glimpses of driftwood washing up on our shores from across the cosmic ocean. And this piece of driftwood, it's made of something we've never seen. The implications for panspermia are also staggering. If this object is carrying complex organic chemistry protected by a heavy metal shielding or crust, it acts as a perfect vessel for transiting biological precursors across the galaxy. The radiation shielding provided by a dense, metal-rich layer is far superior to loose ice. If 3I Atlas is a standard member of the interstellar population, it means the galaxy is filled with armored seeds. It's 2:15 a.m. now. The monitor is refreshing. The spectral lines are still there. Nickel, no iron. It's real. I'm going to pour another coffee. We have a lot of work to do. It is rare that we get to see a puzzle piece from another box. Usually, we are just assembling the sky and the ground of our own little puzzle. But 3I fits nowhere. It reminds me of the first time we analyzed the moon rocks and found they were dry as a bone. It shifted our understanding of the moon's violent birth. 3I is going to shift our understanding of planetary death, because to get a core fragment this rich in specific metals, you likely have to destroy a world. We are looking at a corpse, a beautiful, shiny, speeding corpse, and it's fascinating. I'll keep you updated as the data comes in. But for now, just look up. You can't see it with your eyes, it's too faint, magnitude 18 or so. But it's there, in the direction of the constellation Pisces right now, moving fast. A traveler, a ghost, a mystery made of metal.